Hello, hello, hello. College Chemistry 2. We have 2 chapters to go, and we're going to get started with Chapter 18. Now, it's Chapter 18 in my book, but the old school books that I gave you that were 10th edition, it's actually Chapter 19. So you'll generally see me write Chapter 18/19 in that is why. So there might be some confusion there. There is homework. So when I post the notes, you can find all of these. So again, with the books that you have, I have some of the numbers are the same in both editions, but then if you see a number and then parentheses, use the one in parentheses because those are the numbers found in the 10th edition, which I gave you, unless you happen to go and purchase the 12th or 13th or 14th edition. You probably didn't. You should watch this video on electric vocabulary, or not, but I thought it was interesting, and it kind of talks about Benjamin Franklin and why some things we call positive and negative, and where the terminology came from. And there's just fun facts. So we would have watched it had we been here, but we're not going to. We're not. I mean, I could click on it, and I bet I get a Grammarly ad. Nope, masterclass. It's masterclass, and then I could click on it. Oh, good. Blah, blah, blah.
They had to wait around 2,200 years before any new investigation.
Yep.
He didn't figure out anything.
There's that guy.
Descriptions of the physics.
There's that guy.
Simultaneously in a battery. Similarly, this electric battery would
Oh, wait. I just realized you didn't even see any of that because Screencastify is only recording a tab and you didn't see any of that. That's okay. You can just skip past that. Just watch it. You have plenty of time. Anyway, this chapter is on electrochemistry, and electrochemistry, hence the prefix electro, is all about electricity. And we know from previous studies in chapter 4 that electrons get transferred in redox reactions. Redox standing for reduction, where things gain electrons, and oxidation, where they're losing electrons. So coupled together, we have the transfer of electrons. So this could be energy released from a spontaneous reaction that we convert to electricity. And so we'll look at batteries where we couple things like lithium or nickel with other metals that will transfer electrons. Or maybe we want to take something non-spontaneous and make it happen. So this is, we'll look at this later, hydrolysis of water. So we're applying electricity into water and it's breaking up into hydrogen or oxygen. Now that is a non-spontaneous reaction, but we're driving forward with electricity. So again, anytime we're talking redox, there is something getting oxidized and something getting reduced. So here's the very first one we looked at. Magnesium and oxygen, we have these half reactions where we show the charges change because some things lose and some things gain. And you might remember, hey, how do I tell? How do I know if it's oxidation or reduction? And just remember, Leo the lion goes grrr! And that's losing electrons is oxidation, and the other one, gaining electrons is reduction. Okay, hit buttons, and moving on. Oh, I don't know why that's there. Typically, you start with number 1, but number 4 decided to pop up. I am working in Google Sheets. I had to export all my PowerPoints, and not everything always works out super pretty. So I'm going to put up all of these. Yeah, that'll make me feel better. This is the review from Chapter 4 on how to deal with oxidation numbers. So again, we use oxidation numbers primarily when we deal with molecules or polyatomic ions where there's not necessarily one charge because electrons are also shared. So if we have a simple ionic equation, then the oxidation number is the same as the charges. That's what number 2 is pretty much saying. But if we're talking about oxygen, hydrogen, fluorine, or other nonmetals, when they're sharing, their oxidation number is dependent on how many things they're bonded to. So it's the charge the atom would have if all the electrons were completely transferred. However, they're not actually transferred. And then all the oxidation numbers will add up to the charge. So again, the main ones to remember were oxygen, hydrogen, and fluorine, -2, +1, -1. If the elements are by themselves, not coupled with anything, then they're neutral and it's 0. So we're going to keep that in mind. So we've balanced chemical equations before, way back in chapter 3, but now we're going to balance redox reactions. And they're going to be a tiny bit different. So for starters, we might have, what about the oxidation of iron 2 to iron 3 going to the dichromate ion, and that getting reduced to chromium 3. And this is an acidic solution. Often, most of these redox reactions we're going to find are in an acid or basic solution. So we're going to start by just writing out the unbalanced form. So we have iron 2 turning into iron 3. We have the dichromate ion turning into chromium. So we want to balance this thing. And so the first thing you could probably pick out is that, hey, there's no oxygen over there. Well, we're going to take care of that. So first, we're going to separate these two. So you wouldn't necessarily have to write it out in this form right away, but we're going to separate it. We have the oxidation. Iron +2 is turning into iron +3. And then we have the reduction, dichromate turning into chromium. Now, since there's no oxygens on the right side, when we're dealing with this, so we have 2 chromiums on the left side, but only 1 on the right. So we can add a coefficient like we would normally do to get 2 chromiums. And now to deal with the 7 oxygens, over here, we're going to add 7 water. So you will specifically add H2O on the side that is lacking oxygen. And so since there's 7 oxygens here, we need 7 oxygens there. Now, that's going to add in these hydrogens, and to balance the hydrogens, we're going to add the H+. Remember, we said this is going to be an acidic solution, and so that's where that H+ is coming from. So if there are 14 hydrogens added on the right, we need 14 hydrogens added on the left. So at this point, in terms of the number of atoms, this thing is balanced. Now, for iron was already balanced, but now we can look at balancing the charges. So remember, you're going to add electrons to whatever side has the higher charge. So of +2 and +3, +3 is higher. And we're adding 1 electron on the right so that they both have the same charge. Now, for the other, we already had -2 and +14. Over here, we had +6. So if we need to bring +14, I counted that wrong. Oh, sorry. So over here, we have a total of +12 when you add these together. To bring it down to +6, we add 6 electrons on the left. So again, we add electrons to balance the charge. And so we want to be able to add these things together, but we need to make sure the number of electrons is the same on both sides. So if you're seeing 1 electron up here, but only 6 electrons on the other, then we're going to scale. So we can make this 6 electrons so that it's going to balance out the other half reaction, but then we multiply everything by 6. So that now that these are the same, go away thing. Now that these are the same, we are going to simply add them together, and then with the electrons canceled out, you have your finished balanced redox reaction. So 14 hydrogens, the dichromate, 6 iron 2s make 6 iron 3s, 2 chromium +3s, and 7 waters. That is our balanced redox reaction. And you can go through and verify that everything's balanced. I don't want to read that. Now, we'll work an example in a moment. But if we were talking about a basic solution, what we would do is for every extra hydrogen ion, we would add a hydroxide to both sides. And I'll show you what that looks like in just a moment. So here's that moment. We have iodide and permanganate in basic solution, giving elemental iodine and manganese 4 dioxide. So this is the unbalanced, and we would like to balance it. So first thing we can do is look at our half reactions. We have iodide turning into iodine, and I've already added a 2 to balance the number of atoms. And then we have permanganate turning into MnO2. So again, we need to balance the number of atoms and the charges. So again, with iodine, all we had to do was add the coefficient for the number of atoms. For permanganate, there are 4 oxygens on the left. To get 4 on the right, we need to add a water. So we add 2 H2O over here, but now that gives us 4 hydrogens. So we're going to add 4 hydrogens, 4 hydrogen ions on the left. So then we need to balance the charges. So again, over here, 0 is larger than -2. So we always add electrons to the side with the higher charge. So 2 negatives become neutral by losing 2 electrons. That's our oxidation. Down here, we have -1, we have +4, so that's +3 in total, and over here it's 0. So we're going to need to add 3 electrons on the left to make it equal 0 to what is on the right. So finally, we need to be able to add these together, but the number of electrons has to match. So think of what's the smallest common multiple between 2 and 3, and that is 6. Well, how do we get 6? Well, for iodine, we multiply everything by 3. For the permanganate, we multiply everything by 2. And so once those are the same, again, we should always see the same number of electrons on both sides. Then we can simply add them together to get our almost final answer. Now, because we said this was in a basic solution, not acidic, for every hydrogen, we're going to add a hydroxide. So 8 H pluses, 8 hydroxides. And if we add it here, we also add it there. Now, what happens when you have H plus and hydroxide? They cancel out to make water. So our final answer is 6 iodides, blah, 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 blah. You can read that. I don't want to read that. I hope that's helpful. Also, thank you for the 3 people who responded to my, do you have any questions? And maybe you should ask a question. And of those 3, 2 people did ask questions. I'm assuming everyone else is just on top of things and you're doing great. I haven't graded the last chapter quiz, but I'm about to. I'm excited. I hope everyone did fantastic. Moving on, let's talk about galvanic cells, sometimes called voltaic cells, named after some people who invented these things a couple hundred years ago. But it's some of the, I wouldn't say the earliest known batteries. Some have been created actually like thousands of years ago, and you can look up some documentaries on all that fun stuff. But here's some of the first like scientifically explained versions of how do you make a battery. So to make a battery, or in this galvanic cell, we have set up a simple redox reaction, but we have separated the reducing and oxidizing agents. So you could take a piece of zinc, this black rod, and just stick it in a copper sulfate solution, the blue stuff, and you would have redox. You would have copper ions stealing electrons from zinc giving away those electrons, and yep, you got a reaction. And it would get hot. Most of the energy would be released as thermal energy. However, we don't want thermal energy, we want electricity. So what we're going to do is we're going to set up a circuit where we separate these components and then we put conductive materials between them. So this is the general basis of a galvanic cell. So we have a piece of zinc stuck in zinc sulfate, and we have a piece of copper stuck in copper sulfate. We have what's called a salt bridge now, and it mentions these cotton plugs. This is just an electrolytic solution. So we need something that can conduct electricity, because if you don't have a circuit, electrons don't like to really keep moving. So what happens is we have, instead of zinc directly giving electrons to the copper ions, the electrons pass through something that we like to power, and that generates electrical work. Now, as it passes through, eventually it doesn't do anything to this copper cathode. It goes into solution, and the copper ions accept the electron, and it deposits onto what we call the cathode. Meanwhile, the piece of zinc, as it gave electrons away, the zinc becomes the zinc ion, and in an oxidized form, it is soluble. So if you were to technically weigh these things, the longer you run this circuit, the piece of zinc metal will get lighter because more zinc ends up in solution. The concentration of zinc ion goes up. Meanwhile, if you were to weigh the piece of copper at what we call the cathode will actually end up getting heavier, and the concentration of copper in solution will go down. And so this battery would continue to run until the concentrations get too high, of copper get too high or too low, and for zinc too high. Or when this piece, normally you wouldn't find these pieces running out. Like, you could measure them, but it's not going to be appreciable huge changes. Now, again, some terms I want you to know. The element that is giving electrons away, that is getting oxidized, we call that the anode. So here we have zinc losing an electron to becoming zinc plus 2. On the other side, the side of a battery of a galvanic cell that is accepting electrons where reduction occurs, that is called the cathode. So again, here we have 2 electrons jumping onto copper ions in solution, which then deposit onto this cathode, and that is the cathode. So together, this is Together, this is zinc and copper ion making zinc plus 2 and copper ion, as you see it in the middle bottom. Again, this is a spontaneous reaction. You could just throw these things together and the same thing would happen, and you'd get the energy released as heat. But by separating them, we then extract the energy out as electricity to do all sorts of fun things, like run cell phones so you can play Candy Crush. So that's, or my 6-year-old now wants it to play Minecraft, which honestly, I've been playing Minecraft with him. I still don't get what's so fantastic, but I'm playing way more Minecraft than I ever thought I would be playing right now. Now, a few terms I want you to know, how the strength of a galvanic cell or a battery, you've probably heard we measured in voltage, cell voltage. So you might, if you're looking at your standard AA, they have a cell voltage of about 1.25, or maybe it's 1.5 volts. Where if you have a 9-volt battery, you guessed it, they have 9 volts, and so that's much stronger. Now, another term for this is electromotive. Cell voltage, electromotive force, and cell potential. They all technically mean the same thing, depending on the industry or the setup. You might use one term more than another, and I'll essentially use them interchangeably. So again, remember that voltage, electromotive force, and cell potential are all referring to the same thing. Again, here you see a really, really old, what's that thing called? I don't know. Voltmeter, I guess, showing the 1.1 cell voltage, cell potential, or EMF of this zinc copper galvanic cell setup. And one thing this is telling you is that these are at 1 molar solutions. And that's something that we're going to look at some today and some in the next video, is that as the concentrations change, as temperature change, then that will affect the cell voltage. Now, one way we're going to take this, we want to diagram it, and it looks like this. So we generally always start with the anode, so the thing that's getting oxidized, so the thing that's actually that gives electrons away, and we have the metal, so that's the actual anode, and then it's in a zinc ion solution. That's where the zinc once it gets oxidized, and then these lines, those are showing the phase boundaries between the anode, cathode, and the solution. Then there's these two vertical lines. That's the salt bridge. Again, that's what allows the conductance for it to conduct all the way around to complete the circuit, and you won't get anything happening without it. And then we have the cathode. Again, the solution, and then we have the solution the cathode sits in, and then finally the cathode. And that bell means it is, let's see, 10. It is now fourth period. Oh, wait, no, it's Tuesday. It's chapel schedule. So I'm looking at the clock. I don't know what that bell means. We would normally be in chapel right now, but we're not. So there you go. Now, what we would like to do, and what we're about to look at, is instead of mixing a random anode and cathode together to come up with a voltage, we would like to standardize this process to say that to take a certain substance, it has this potential. Now, if you remove one of either the anode and cathode from this apparatus, this setup, you will have zero voltage. So you can't say there's a cell voltage for just copper or just zinc. So it requires the pairing to be meaningful, but we don't like to always have to set stuff up. So instead, we're going to set up a standard reduction potential. So that's the word standard means we're going to selectively choose something to have a set value. So again, we have that superscript 0, E naught. That tells us it is a standard reduction potential, as opposed here is non-standard. So we're going to take the reduction potential of all solutes at 1 molar at 1 atmosphere. Now, it's impossible to measure these things by themselves. Again, it's not meaningful. You can't have a potential if if you can't go from here to there, then you don't. That there is no measurement. So we can't measure just one. However, we're going to use a reference to compare. So we're going to compare with She, capital SHE, which stands for the standard hydrogen electrode seen right here. So if you take a 1 molar hydrochloric acid solution, stick into it a platinum electrode, and then check the conductance where hydrogen is oxidizing platinum, platinum is reducing hydrogen. We have decided, and by we I mean like some people 100 years ago, to set this voltage to exactly 0. Now this is very, 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 very similar to when we talked about standard enthalpy and standard Gibbs free energy, where we said, hey, what is the standard enthalpy of hydrogen gas? And you'd say, oh, it's 0. Or what's the standard Gibbs free energy of hydrogen gas? Oh, let's make that 0. And then we could compare things above or below it depending on their energetics. So again, using hydrogen as a standard, the amount of energy or the voltage needed to reduce hydrogen to hydrogen ion to hydrogen gas is set at 0 volts. And so then what we do is we measure things in comparison to hydrogen. And we are going to set up standard reduction potentials for pretty much everything. There's a whole bunch of them. So let's say we take our standard electrode of hydrogen and we couple it with zinc sulfate. So we have the zinc, the zinc electrode and zinc sulfate. Again, this here is our salt bridge, and then it's an acid solution and with a platinum electrode to make it conductive. And we measure, oh, and then there's some stuff. Yep, oxidation, reduction. So if we do this, we will measure a standard reduction potential of 0.76 volts. Now, keep in mind, this is technically for both zinc coupled to the HCl. Well, here's a fun equation that you're going to need to know, and we're going to be using a lot in this chapter. So the standard cell potential is the cathode minus the anode. These zeros should be a little further to the left. That's bothering me, but I'm not going to fix it right now. Nope, not going to do it. So remember, the cathode is where reduction happens. And in this case, your cathode is going to be hydrogen. So it's the thing that's gaining electrons. And the anode is where oxidation happens. In this case, it's going to be zinc. Now, we've collectively been able to, we can very easily measure the cell potential to be 0.76. And we have set the value for hydrogen to be 0. So using this, we can now say the standard reduction potential of zinc is negative 0.76 volts. So this value tells us something about zinc and how likely it is going to react in a redox reaction, or how well it's going to want to give electrons or take electrons compared to something else. Okay, let's look at another one. So now let's compare that HCl electrode with copper sulfate. Notice, again, I'm going to switch back and forth. Over here, they're showing HCl, the cathode, on the right, but over here it's on the left, and that's because this time HCl is, instead of the cathode, it's the anode. So with zinc, zinc can give electrons to hydrogen, but compared to copper, copper can only take electrons from hydrogen. Hydrogen gives them to copper, so it doesn't. In this case, hydrogen is switched. So we do the same thing. We set this up, and we get a voltage of 0.34 volts. And going back, it's cathode minus anode. So we've measured the standard electromotive force to be 0.34. And we know that hydrogen has been set at 0. So now we can say the standard reduction potential of copper is positive 0.34. Again, notice that it's a positive value compared to zinc was like negative 0.7. And so the higher the value, we're going to see that it's more likely to become oxidized. So here is something it might be easier to look this up in the book than to try to look at it in the notes. And there's actually a larger table in one of the appendices at the very back of the book. But this chart shows pretty much all of the ones you'll need, but there's more than this. Class is something. I don't know what it means. Doesn't matter. But it's showing all of the reductions of different elements, different ions. There's some polyatomic ions. There's a few molecules in here. And it's showing what would be the cell voltage required for that to happen. So for fluorine, for fluorine to get reduced to fluoride, it's 2.87. Whereas for, let's see, cadmium ion to get reduced to cadmium neutral, it's negative 0.4 volts. So each one of these is written as a reduction, so not oxidation. And the more positive, so the things at the top, these are more likely to get reduced. Whereas the things on the bottom, they're more likely to go in the reverse direction. Now, back in chapter 4 last semester, we looked at what was called the activity series. And this is pretty much just an expanded version, but it goes in the exact same order. Where with the activity series, we said whatever metal was higher could displace whatever metal was lower. And this is just a more quantitative way of looking at it. So the more positive it can reduce and oxidize something on the right side lower than it. Often you hear with this the diagonal rule. So essentially all this means, where's my diagonal? I don't know, it'll pop up at some point, is imagine a diagonal from the top left to the bottom right. So oxygen can oxidize copper 1 into copper 2, but not the reverse. Copper 2 can oxidize cadmium into cadmium plus 2, but not the reverse. So whatever is higher can get reduced and oxidize whatever ion is lower, so it reverses. Now this next bullet says the half cells are reversible. That's true. So if I'm going to say that the silver ion can oxidize cobalt to cobalt plus 2, you can reverse this reaction, and similar to what we did in our other thermochemical chapters, if I reverse the direction, I change the sign. So instead of negative 0.28, it is positive 0.28. And that's what that says. There's the arrow. So yeah, again, whatever is higher on the left can oxidize whatever is lower on the right to make it go in the reverse. Now, one thing that's different, when we did some thermochem with Gibbs free energy, and more specifically enthalpy, if there was a balanced equation, we would use the coefficients to scale the numbers. We don't do that here. So we don't care about the coefficients. It does not change the value of the cell potential. So let's try using it. So we want to know what would happen if you add molecular bromine to a solution of table salt and sodium iodide at 25 degrees Celsius. Basically, if it doesn't say a temperature, you should always assume 25 degrees Celsius. And we're assuming everything is in standard state. So that's also 1 atmosphere. So the first thing we want to do is we're going to go back to that table and see where do bromine, chloride, and iodine line up. So let's do that. So here's bromine. Oh, can't click you. Bromine has a value of 1.07, positive 1.07. Okay, so then we need chloride. Where are you at, chloride? I'm looking. There you are. Chlorine has a value of 1.36. And then iodine has a value of positive 0.53. So here are those values written out. So again, each one of these, where's the arrows? Each one of these are written as reductions, as gaining electrons. So they're all positive, meaning they all normally like to get reduced. They like to oxidize other things, but how does bromine compare? So again, we're going to say the higher the value, the more likely it can oxidize lower values. So we can say that bromine can oxidize iodine because 1.07 is higher than 0.53. However, it will not oxidize chlorine. So when bromine is added to a table salt solution, nothing happens because chlorine has the higher reduction potential. But that's not true for the iodine. So here's our overall reaction. Iodine or iodide and bromine make iodine and bromide. So to calculate our cell potential, all we have to do is subtract. It is cathode minus anode. So recall that we're going to say that the cathode is the one getting reduced. And we're subtracting the anode, that's the one getting oxidized. So if bromine had a value of 1.07 and our iodine had a value of 0.53, by subtracting, we get a value of 0.54 volts. And that, again, that would be our expected measured voltage if we set up a galvanic cell. Okay, let's try this again. So we're setting a piece of magnesium in magnesium nitrate. We're setting silver in silver nitrate. And again, standard conditions are 1 molar. We want to know what's the standard EMF, which is the same as cell potential, which is the same as cell voltage. So we first need to figure out in what direction is it going to go. So we go back to that table and we find for silver, it's 0.8. But for magnesium, it's negative 2.37. So that means silver really likes getting reduced. The higher the value, the more likely it wants to get reduced. But magnesium does not. So when we mix these together, we can go ahead and expect that silver will go in this direction, but magnesium is going to be reversed. So again, the diagonal rule would be that the silver ion will oxidize magnesium neutral. And so here's that written together. Magnesium and the silver ion make magnesium ion and elemental silver. But to figure out the cell voltage, again, it's all we have to do. And then notice, for the sake of balancing, there was a 2 added to silver, and then there's 2 electrons, 2 silvers. But even though we added that 2, it is not going to change our standard potential at all. So we looked up the values. Oh, things are coming out weird. That's what I wanted first. So our standard potential is it's always cathode minus anode. So the cathode is this, in this case, silver, the thing that's getting reduced, and then we're subtracting magnesium, the thing that's getting oxidized. So it's what's getting reduced minus what's getting oxidized. So reduced minus oxidized. And so looking in the values, we get a positive 3.7 voltage, which is pretty high. That would make a fantastic battery. Too bad silver's really expensive, so that's one of the reasons why we don't use it. Oh, here's a neat video. How do fish generate electricity? You should watch it. It is, I would say, 25% relevant to this chapter because of the electricity part, but I just thought it was interesting, and I was looking for videos to stick into this class, even if they didn't completely apply, but because I just thought we need more videos. So you should watch that one, because I know you have extra time, so you should do that. Now, the last part for today, or tomorrow, or however, is relating the cell potential that we've been calculating to Gibbs free energy, standard Gibbs free energy, which was in the last chapter, and everyone's favorite, the equilibrium constant. Yay! Sorry about that. And so we're going to see that if we want to talk about the spontaneity of a given reaction, we can compare all 3 of these to get, well, we can go from one to the other to the another and then figure out spontaneity. So to do that, there's a little bit of groundwork we have to talk about. So this is really more physics. Electrical energy, anytime it's energy, we're measuring in joules. Now to get joules, the electrical, it's the charge times the cell potential, where charge is measured in coulombs. That's your standard unit of charge, base unit of charge, and potential is measured in volts. So coulombs times volts gives you joules. And so 1 joule is coulomb times a volt. One moment. So 1 joule is a coulomb times a volt. Now, the charge of an electron that's getting transferred is really small. It's like 1 point something times 10 to the negative 19 coulombs. And we're not usually talking about just a single electron, like in a given reaction that we're actually carrying out. Instead, we're talking about moles of electrons, because we deal with moles of quantities. So we're going to use this term, capital F, known as Faraday's constant. And it is the charge of 1 mole of electrons. So if you take the charge of 1 electron, multiply it by Avogadro's number, you get this 9.65 times 10 to the fourth coulombs. Again, this is the total charge for 1 whole mole of electrons. Now, to see how much work, electrical work, a redox reaction can actually have, we then look at this. So remember what N is. N from the ideal gas law and other things. N is how many moles of something there are. So if F is the charge per mole, then N times F is the total charge. So NF is actually just the total charge in volts or in coulombs of the electrons being transferred. Okay, well then E of the cell, this is our cell potential. So we have coulombs times volts gives us joules. So if we have this value, and there's a negative because we're saying this is anytime you do work, you're lowering your energy level. So negative NFE, this is the amount of available electrical work. So if we figure out how many electrons are being transferred, and we're talking about mole quantities worth of charge times the cell voltage, then we can say, well, this is how much work can be done. Oh, and there's those constants. Now, what we're going to do is relate this to delta G. So delta G was our Gibbs free energy. So if this is the available electrical work of that can be done, well, that's what Gibbs free energy represents, is how much energy is available to do work. So we can set this product equal to this standard Gibbs free energy. So in the last chapter, we had this relationship. We said you could relate Gibbs free energy to the gas constant times temperature times the natural log of the equilibrium constant. And I hope you see where we're going here. So if this equals this, and this equals that, and these two equal, we can then relate all of them. So with these two linked, we can then say the cell potential, standard cell potential, is equal to the gas constant times temperature divided by the number of electrons transferred times Faraday constant, which is, again, together just the charge times the natural log of K. Or if you don't like the natural log, oh, and there's some other stuff, blah, blah, blah. Yeah, the units. If you don't like that, the natural log, you could also use the standard log, log base 10. And either one, you get these two bottom equations. These two are generally provided on assessments, or on take-home stuff. I probably won't. You can just look it up. But notice it couples our the gas constant along with some other stuff. So 0.0257 volts divided by N times the natural log of equilibrium, or 0.0592 volts divided by N times the log base 10 of the equilibrium constant. Either way, we can then use this to tie all of these things beautifully together. Isn't that nice? So first we had the equilibrium constant. Then we talked about Gibbs free energy, and now we can then relate it to standard cell potential, again, if we're talking about a redox reaction. Isn't that nice? So we've been able to say now 3 different ways whether a reaction is spontaneous or not. So the main ones, again, here's our relationship. We've said before that if Gibbs free energy value is negative, then that means there's this leftover energy. It can proceed forward. It's spontaneous. Or if we say K is greater than 1, that means it's favoring the reactants. And now we can also say if the standard cell potential is positive, it's going to favor the formation of products. Whereas we could also then say if it's at equilibrium, if this is 0, this is equal to 1, or that's 0, and it's not likely to go forward, wait a second, that's supposed to be an X. Okay, just imagine that as an X. I don't know why it turned into a box. Oh, Google Sheets. Doesn't matter. So if it's positive, if K is less than 1, if standard cell potential is negative, then it favors the reactants, which means it's going to go in the reverse of the way you've drawn it. So what we're going to do now is practice a few more problems. We're almost done. I promise, I think. I'm not actually sure. I know where I'm stopping. I think we're almost there. So we have tin added to copper, and the copper ion, and copper ion is getting reduced to copper from 2 to 1. Tin is getting oxidized from tin to tin plus 2. And we want to know, what is the equilibrium constant? So what we can do with our standard reduction potentials is calculate this. So we can calculate the cell potential by looking up those values. And then we can use this expression to figure out what is this constant K, our equilibrium constant. So let's say we go back to that table. I did. You can do it later for other problems. And we look up for tin. For it to get reduced, its potential is negative 0.14 volts. But for copper 2, it's getting reduced, its reduction is 0.15 volts. Now, just looking at these values, you would normally expect the copper 2 to then not want to get oxidized. I'm getting a phone call. I'm going to pause. Got a phone call. A student's coming over. I don't know why. Why would they think I was here? I mean, I am here. But, I'm going to try to finish this up. So normally you would look at these cell potentials and say, well, if copper 2 has the larger value, it's the one that's going to want to get reduced. And that is, in fact, the case. So we look up here and see copper 2 is getting reduced to copper 1. So that is going to be our cathode. It is getting reduced. However, even though we wrote out tin 2 getting reduced, up here, it's written as what's getting oxidized. So whatever's getting oxidized, that is always going to be our anode. So knowing this, again, it's always going to be cathode minus anode. So our copper had the cell or standard potential of 0.15. We subtract the anode potential of negative 0.14 to get 0.29 volts. Now, the fact that this is positive already tells us that this reaction can happen spontaneously. So all we have to do now is use our fun equation. So here's our cell. So here's that equation rearranged. So 0.29, what's N? N is how many electrons are getting transferred. And from the half reactions, we see there are 2. So 2 times 0.29 divided by the constants, all of this equals 22.6. And that is equal to the natural log of K. Now, how do we get rid of the natural log? Euler's number. And so e to the 22.6, we get a very, very, very big number. So that's 7 billion. So again, this 0.29 is positive, tells us it's spontaneous. Same thing, the fact that K is greater than 1 and really, really bigger than 1 would tell us that, yes, this is a spontaneous reaction. Okay, last problem for today. So here's another one. Gold calcium ion making oxidizing gold, reducing calcium. So we want to know what's the electromotive force, and we can use this relationship to get it, so that the Gibbs free energy is negative NF cell potential. Now, okay, so we have gold getting oxidized, losing 6 electrons. We have calcium gaining 6 electrons, the ions getting reduced. And again, our gold is our anode, our calcium is our cathode. So going through and subtracting out cathode minus anode, we have calcium, we subtract the gold, and we get this negative 4.37 volts. So as we talked about earlier, the fact that this is negative tells us this reaction is not spontaneous. It is not likely to be favored. And so now we can see, well, how does that coincide with the Gibbs free energy? So bringing up our equation that relates it, N, if you might recall from our half reactions, was 6 electrons total. F is the Faraday's constant, and E is what we've just calculated. Then we get 2.53 times 10 to the 6th. And so that is 2.5 thousand kilojoules per mole. And I mean, that is a very large number, but more importantly, the sign that it's positive still tells us in terms of Gibbs free energy, it would not be favored to happen. And instead, the reverse is much, much, much more likely to happen. Okay, with that is the end of part 1 of this chapter. And tomorrow or the next day, I'll post the second part. And you can expect, similar to last week, you can expect the next quiz probably given out Friday to be turned in on Monday.